Using a heap file with an unclustered hash index, we also have two files. One heap file of data records and one index file of hashed data entries pointing to those data records. For our discussion of unclustered hash index, let's make the simplifying assumption that we do not have additional linked buckets. Also, based on empirical data, let's assume that in the hashed file, the pages are kept at 80% occupancy for leaving a space for future insertions. Therefore, the number of pages required to store the records in B-packed pages will be 1.25B. Again, we make the assumption that the size of data entries in the index file are 1/10 of the size of actual data records. Using the 80% occupancy and 1/10 of length of data records, the number of data records on a page will be 10 times 0.8, which is 8R. Now, let's use these assumptions and calculate the costs. The scan of the heap file using the index file is going through all the index data entries and fetching the corresponding data records. This is going to give us the records in a sorted order. Reading all the entries of the index file will take 0.125B times D plus 8RC. However, similar to the unclustered tree file, the expensive part in this operation is also fetching each record for the data entry in the index file, which is BR times D plus C. If we remove the negligible parts from the estimation and keep the cost of I/O only, we can estimate the cost of a scan with BD times R plus 0.125, which is again quite high. So no one really scans a hash index, as it will have higher costs than storing the data records file. For a search with equality selection, the cost of identifying the page that has the data entry is cost of applying the hash function, which is H. Remember, we assume that we do not have additional linked buckets. So accessing the corresponding page will only cost D. Then finding the data entry on that page, on average, will take scanning half of the records, which will be 0.5 times number of records in a page, which we said is 8R, times C, which is the time to process each record. Finally, we have to fetch the data page from the data records file, which adds another D to the equation, bringing the cost to H plus 2D plus 4RC. Note that given H and RC are small, the greatest element of cost is 2 I/O operations needed with cost 2D, and therefore this is quite efficient. For range selection, the hash structure offers no help, and the entire heap file must be scanned with the cost of B times D plus RC. For insert, the record is first inserted into the data records heap file at the cost of 2D plus C. Then the appropriate page in the index file is located, modified, and written back. The cost of locating the bucket is H, which is cost of applying the hash function, plus the cost of D for reading the page, C for record processing, and another D for writing the page back, which brings the total cost of insert to 4D plus H plus 2C, with the dominant cost of I/O equal to 4D. Delete operation includes finding the record updating its index page and updating its data records page. This adds a D for each update, bringing the total cost of delete operation to that of cost of search plus 2D.